It's a very nice place to work at. And so I will indeed report with a recent joint work with Michael Brannan from Texas A&M, which is about, well, actually where we proved that orthogonal frequent and group factors are not isomorphic to free group factors. And this uses tools from the theory of free entropy dimensions. So some of you already know quite a lot about orthogonal frequent and groups, but some of you don't, and don't know who knows what about free entropy. So I think I will try to explain a little bit what are these objects we are interested in and what kind of questions we want to answer. And then I explain the tools that we use and our general strategy, but I don't think I will go into the technical details. So let me start with a few words about these objects. So say orthogonal quantum groups, or orthogonal frequent groups. Well, actually, it's just an algebra that we want to study. And the definition is very easy to write down and very natural, at least at the full system algebra level. So the definition is as follows, and it's due to Wang. So there is a unital system algebra denoted A of n. So n is an integer parameter, which is defined by generators and relations. So the universal system algebra with a unit and generated by n squared elements that you denote uij, and which should satisfy some relations. So in this orthogonal version, they should be self-adjoint. And the most important condition is that they should form a unitary matrix. So u star equals u star u equals 1. And here, so u is the matrix of the generators. So this lives in Mn of n. And these unitary conditions, you can write them down explicitly. These are 2n squared relations, polynomial relations between the generators, and actually I'll come back to that later in the talk. So this is a well-defined system algebra, which is very natural. It's kind of an analog of free group algebra. And instead of having n generators which are independently unitary, you have a matrix of generators, and this should be unitary as a whole. So this is very natural, I think. And you want to study this algebra. And a very useful fact to study this algebra is that there is some group-like structure on it. And what I mean by group-like structure is actually a star homomorphism. So delta from the algebra to its tensor product with itself.
Do you have transpose?
Sorry?
Definition?
Yeah.
In the star involves transposition
there is no transpose, but
uij star is uij.
Yes.
Not uji.
No. So the elements. So it's like an orthogonal matrix. I mean, if the uij are complex numbers, what you get is an orthogonal matrix. And there is a unitary version also of this algebra. For today's talk, I concentrate on this one. And okay, so so there is a star homomorphism which is defined on the generators just by mapping uij to some dualizing matrix multiplication rule. So sum of uij consider ukj. And you have to check that this is well defined, but it's very easy to do. Okay, and so what is this group-like structure? Well, first of all, I will make the connection with classical groups. So there are interesting quotients of this algebra which make the link to classical groups. So the first one is onto the algebra of continuous functions on the usual orthogonal group ON, so the group of matrices, and which is just the Abelinization quotient. Okay, so you say, if you want, you say commutators between generators to 0. And what you obtain is a system algebra isomorphic to C of O. Okay. And the point is that this map here goes through the quotient. So it's compatible with the quotient prime is compatible with delta in the sense that you can pass to the quotient and you obtain a map delta at this level. And which is very easy to write down. So this is isomorphic to functions on 2 variables. And the formula is delta of f as a function here maps Rs to f of Rs. So this delta at the level of C of O reflects really the group structure on the classical group. Okay, this is one point, and this somehow motivates a notation which is sometimes used. Sometimes we think of A of n as an algebra of non-commutative functions on some compact space, compact quantum space. And so sometimes we denote A of n equals C of O(n+), where O(n+) is some compact quantum group, in fact.
So why do you write a 0?
The small O here is for orthogonal. Okay. So there is AO and AU for the unitary version. I mean, there is a whole story of notation within this business, and I had some argument with Giovanni a couple of weeks ago about that. Maybe some of you also had it. Okay, there is another interesting quotient map onto a group system algebra, namely the universal group system algebra of the free product of Z over 2Z with itself n times. Okay, free product n times. And this is obtained by mapping the off-diagonal generators to 0. So Uij goes to 0 if I is different from j, and the diagonal generators, they go to the canonical generators in there. Okay, and this time, again, the quotient map is compatible with the map delta, and what you obtain is a map from this algebra to tensor product with itself, and okay, so let's write it. So you get again a map like that. And in fact, the point is that you can use this map to recognize the group elements inside the algebra. So, in other words, you C over 2Z, C product n times, can be recovered as the set of unitaries in the algebra which satisfy the equation delta U equals U tensor U. Okay, so again, the delta allows you to recover a group inside the algebra. So the group law is given by the product in the algebra, of course, but you need to recognize the group elements, and this can be achieved using delta. Okay, and this picture, I mean, if you, so this quotient map at least motivates another notation. And this time, the point is that you would like to think of AU of n as the sister algebra of some discrete group, not an algebra of functions, but group algebra. Okay? And so the associated notation is C-star universal of F1, and here you have a discrete group object. So this is again just a notation, which was introduced by Christian.
Tim doesn't like it?
I like it very much. And we use it in the paper with my
Tim?
You should discuss this with him. It will be interesting, I think. Okay, never mind. I mean, it's just, but I mean, it's a nice notation because it allows to remember the parallel with usual discrete groups and group algebras and that kind of thing. Okay, well actually, so there is a whole theory behind that kind of object. So just let me write one definition, which is probably the right framework for that kind of things. So the definition is the one of the Voronov sister algebra. So it's a unitary sister algebra and a star homomorphism from A to A tensor A, and this is the minimal tensor product here, homomorphism, with two actions. So delta identity delta should be identity tensor delta delta, and this is called co-associativity, and there is a density action, delta of A, one tensor A, and delta of A tensor 1 should be dense in A tensor. Okay. So this is a very simple definition, and there is a very rich theory that you can develop from this definition. And okay, so and then I mean, the idea again is that A is the algebra of non-commutative functions on a compact quantum group G, or some quantum group sister algebra. So this is the compact quantum group, discrete quantum group, which are in duality in some sense. But this is, I mean, it's just an algebra. Okay. And one of the first theorem in the theory, which is due to Roland, is the existence of a distinguished state, which is called the R state. So there exists a unique state H, which is invariant with respect to the coproduct delta. So this means H tensor identity delta equals identity tensor H delta equals H times 1. Okay, so you have a natural distinguished state on that kind of algebras. And once you have this state, of course, what you do is you perform the GNS construction. Okay, so GNS construction gives you well, a representation onto some Hilbert space, say capital H. And you can look at the bicommutant. Okay, so we will denote in the case of FON, at least, so in the case of this algebra introduced by Jung, I will denote L of FON, the bicommutant of the image of this representation. Okay, and it's really, I mean, the analog of the phenomenon algebra of a discrete group, but in the quantum case. And this is the object that one wants to study, which actually has been studied a lot for 2 decades, I think, and many things are known about this phenomenon algebra. So, well, first of all, it's non-injective, and that was the first result by Manika, and then together with Stefan Raas, we proved that it is a 2-1 factor, which is full, and which is solid, all that kind of things. And then it was proved to be strongly solid by Zono, and also myself. So, and there are also approximation properties that are known. So the so-called Hagerup approximation property was proved by Michael Brannan. The completely bounded approximation property was proved by Roland Vergnioux. Okay, so it's a bit now understood somehow, but and so if you know about phenomenon algebras and 2-1 factors, you might have noticed that all the properties that I just quoted are also true for free group factors, for the usual free group factors. And so in fact it's been an open question since 14 years maybe or more, I don't know. So the question was, is it possible that it is in fact isomorphic to a free group factor? So here, Fk is a free group Poynting generator. And as you might know, these kind of questions are quite difficult in general. And this is the question we answer in the negative. So as I said, we use tools from probability of the theory of free probability, and actually there are also results. I mean, from free probability theory that were already known about this algebra. So, so for instance, it was known that in the large n limit, the generators uij, so they become free and semicircular as n go to infinity. So the moments, if you want the moments, the joint moments of these variables, when n go to infinity, with respect to the half state, I should say, okay. So with respect to h, the moments go to the moments of a free semicircular family. But this is only in the large n limit. But somehow this shows that there is some freeness there. Okay, then I mean, I think the first hint that these algebras might not be isomorphic to free group algebras came from the computation of the first n2 number. So this is something I did some years ago. So the first n2 number for these discrete quantum groups vanishes. And this implies by deep results of Cohn and Giardenko that the free entropy dimension of the generators, delta 0, I will say a couple of words about that later, is less than or equal to 1. On the other hand, together with Mike and Benoit Collins, we proved that L of F1 is Cohn embeddable. So the generators, in other words, the generators admit microstates. And so this implies, again, by a deep result by Cayley Jung, that the free entropy dimension is larger than or equal to 1. So in fact, it's equal to 1. And as you might know, if you look at a free group and at the standard generators, the free entropy dimension is Cayley. I mean, it's been constructed for that reason, I think. Okay, so this was a hint that the fundamental algebras are not isomorphic, but of course, I mean, it's not known. It's probably the most important open problem in free probability theory. It's not known whether delta 0 is an invariant for the fundamental algebra. Okay? It's only known to be an invariant for the star algebra generated by elements. So this does not disprove isomorphism, and the point is that there is a slightly stronger notion which is due to Cayley Jung, and that I will explain a little bit, and which is an invariant of fundamental algebras. So invariant of fundamental algebras. This is called strong one-boundedness. And so the theorem that we prove that with Michael is that L of F1 is strongly one-bounded. So this is a reinforcement, if you want, of this inequality here. And as a consequence, by results of Cayley Jung, it cannot be isomorphic to a free factor. Or it can also, I mean, it's not isomorphic to free group. Yeah, it's not isomorphic either to another one which might be natural in that context, which is the free product of copies of the two. So it cannot be isomorphic either to such a nature. Okay. So now, I mean, the next open question that I would like to ask, that's probably much more difficult, is does there exist at all discrete group gamma which has the same fundamental algebra? I mean, we have a excluded somehow the most natural candidates. So you might think that, in fact, this cannot be a discrete group phenomenon algebra. But I have no idea. I mean, it's probably very, very complicated. There are some candidates. I mean, if you look at, I think, at ICC lattices in the SL2C, there are phenomenal algebras, and of gamma satisfy all the properties that are known for orthogonal frequent group factors. But, I mean, it doesn't look very natural, but who knows? Okay. So now I'd like to say a few words about free entropy dimension and how we can use it. So there is a whole theory due to Vergnioux of free probability, free entropy dimension. I won't say much about that, but so the point is, so the setting is, general setting is as follows. So you have a phenomenal algebra equipped with a trace, so a finite phenomenal algebra. So you have the associated L2 space, capital H. And you look at self-adjoint elements inside M, so X is the tuple X1 to Xm of self-adjoint elements. Okay, and then there is a notion of free entropy. Actually, there are many or more than one notion of free entropy. Say, so K of X, free entropy, so this is free entropy. So this is a number, possibly minus infinity. And there are, as I said, there are a couple of versions. So the original definition was in terms of microstates. Then there is a non-microstate approach, which uses conjugate variables, kind of things. I won't go give you the definition because it's quite technical, and if you have not seen it before, I don't think it's very enlightening. The point is that it's a number which is supposed to somehow to measure the amount of freeness in the sense of free independence with respect to the trace between these elements x1 to xm. So, for instance, I can say one thing maybe. So if the two norm of x is fixed, the quantity is maximal, the free entropy is maximal, if and only if x is a free semicircular system. Okay, so you have this number. But it's not an invariant even of the star algebra generated by the xi's. So out of this quantity, you can build something which is more invariant, which is the free entropy dimension. So, and I will write the difference. Yeah. So the free entropy dimension and maybe I should work with let's put a star. So maybe I should work with the non-microstates version. So delta star of x. So what you do is you regularize the tuple. So I will write it down below, but you look at chi of x plus delta s, and s is again a tuple. Also self-adjoint elements in M, which is a free semicircular family, and also free from X. So you can always assume that you have such a family inside M by enlarging M if necessary, replace M with a free product if you need. And so then you regularize, and you You divide by log of delta, and you put delta inf. As delta goes to 0, so you kind of cut off the regularization, and you look at the asymptotic behavior. And you put m minus, so that it looks nice. Okay. So this is the free entropy dimension. And as I said, for a free group factor, together with the standard generators, you recover the number of generators, which is nice. Okay. Okay. No. So as I said, it's not a fundamental invariant. But there is this notion by Jung. So that I want to explain a little bit, so that you see what happens, and it is a little bit technical, all these kind of things. So, the remark is that the delta star is less than alpha if and only if chi star of x plus delta s is less than m minus alpha. Log delta with an absolute value here, plus a small o of log delta. So this is a reformulation, straightforward reformulation from the definition. Okay, so this is one thing, and then the definition by Jung is that x is said to be alpha bounded. Say for chi star of delta. So here I'm dealing with the non-microstate version, but you can do the same definition with microstates. If you have the same estimate, so chi star of x plus delta s is less than that thing. And you replace the small o of log delta, which can still go to infinity as delta go to 0. You replace it with a constant for small delta. So this is really a technical modification, which is about the remainder term, okay, in the asymptotics of chi of x plus delta s. And so I mean, this looks very technical, and it is in fact quite technical. And using this reinforcement, Cayley Jung was able to prove the von Neumann invariance, which is still open for delta star or delta 0 itself. So the statement is following one: if x is 1 bounded, so this only works for alpha equals 1. And so there is this strongly 1 bounded. So strongly means that at least one of the xi's has finite entropy. So say chi of x1 is finite. Then for any other tuple of generators of the same fundamental algebra, so if you have W star of x, so this is the generated fundamental algebra, if it is equal to some W star of y with another tuple, say n prime, then this other tuple must have delta star. Well, actually, it should write delta 0 less than 1. So this was proved, I mean, stated and proved by Jung in the microstates setting. But anyway. Okay, so this is a fundamental invariance. You can change the generators inside the generated fundamental algebra. Okay, so this is quite deep. And this is what we used. Now,
I'm sorry, why
yeah.
the free entropy or free intervention are not fundamental?
It's not
depends on what.
It's not known. I mean, if it's a fundamental invariant, that's the big question. But it's known to be invariant for the star algebra. So the delta 0. If you change the generators by taking star polynomials, you will get the same number. But if you take generators
Yeah, that was
of fundamental algebra in the larger fundamental algebra, then it's not known whether delta zero. And of course, if it was known that delta zero is invariant, it would solve the field factor isomorphism problem. So maybe it is. I mean, but right now we just have this tool, one strong one particles, which is somehow a technical variant. Okay. Now the question, I mean, since I didn't give the definition of free entropy to you, I mean, the question is how to prove that kind of things. And the point is that there is a tool which was introduced recently, again by Jung, and then reproved by Chilartenko, which allows to prove that some double is alpha-bounded, say. And this is this tool that we used, so not the definition directly. So I will explain you how the tool works, and it's I think understandable. So the tool has to do with an algebraic object, which is the free difference quotient by Roland again, which is easy. So so how to prove alpha boundedness? And so you have to make some algebra. So we use Cx, so C bracket x. So this is an algebra of polynomials, but with non-commuting variables. So algebra of polynomials in n non-commuting variables. So x is again the tuple of the indeterminates. And so you have these three difference quotients, three different derivations, del I, which go from Cx to tensor Cx, and which are derivations, so here, I mean, you have natural bimodule structure over Cx. Okay, Cx is on the left of the left leg and on the right of the right leg. And it's a derivation, and the value on the generators is as follows. So xj is mapped to delta ij, 1 tensor 1. Okay, so derivation, star derivation. So this is the algebra, but the xi's are supposed to be self-adjoint. And okay, so it's something which is very easy to compute. I can give you an example. So you want to compute, say, del 1 of x2, x1, x3 squared, x1, x4. Okay, what you have to do is to, in fact, to look at all occurrences of x1 if you work with the d1, and in fact you replace the occurrences of x1 by a tensor product, and then you sum over the occurrences. So what you get is x2 tensor x3 squared x1 x4 plus here I have two occurrences x2 x1 x3 squared tensor x4. Okay, so you have that kind of rules. So it is quite easy to compute. Okay. Now we don't take just one polynomials, but a collection of polynomials. So we take p in Cx to the power L. So L polynomials, and then we put all three derivatives together. So we denote del p equals Lj pi. So this will be Cx, tensor Cx. And it's a matrix, tensor of, I hope I'm right, Cm, Cl. That's one. So if you start from a collection of non-commutative polynomials, you can build this matrix. And then if you have elements in a fundamental algebra, you can evaluate the polynomials at the elements of the fundamental algebra. So you can look at delta p evaluated at x, and this will be an operator acting on H tensor H, okay, the L2 space of the fundamental algebra. So Cn and the same. Okay, so this is evaluation. So you let Cx again act by left multiplication on H on the first H, and the second Cx act by right multiplication on the second copy of H. And the point is that you still have a bimodule structure inside. So you can still act using M on, or M opposite, on the right of the first leg and on the left of the second leg. So this is a, I should write maybe M tensor M opposite linear with respect to this, the two other actions of M that you have there. And so you can use fundamental dimensions. And so we denote rank of delta px, the dimension over M tensor M op of the closure of the image of this operator. So it's a right module over M tensor M, if you look carefully. And so you have fundamental dimension, and this is a number. Okay, and then these are the ingredients. And then the theorem proved again by Jung in the microstates setting, and then reproved by Sliartenko in the non-microstates setting, is the following one. Sliartenko. So you have to start from polynomials which are actually relations. So you start from polynomial relations between the elements x, I. Okay, so you suppose that p of x equals 0. You start from polynomial relations, and there is an analytical hypothesis, which is that del p of x should be of determinant class. And I will explain later what it is. Then x is m minus the rank bounded. That's the tool. Okay, so it's it's quite tractable. You have to manage to compute a fundamental dimension, etc. But this is something that can really be used, and this is what we used. So so now I'll come back to FON, and I try to explain how we used this this tool. So back to FON. So again, so we look at the fundamental algebra associated with FON with the R state. Okay, so we need generators and relations, but of course we already have them. I mean, we have the standard generators. So we will take x equals u actually, okay? So x equals uij. So this means that little m is equal to n squared. And the indices are matrix indices, but okay. And we also have canonical relations. So these are the relations that are used to define AON. Okay, so they are used to define the full sister algebra, but of course they are still true in the reduced sister algebra and in the fundamental algebra. So as I said, we have two n squared relations. I mean, writing that the matrix is unitary, gives you two n squared relations. So L is 2n squared, and the corresponding polynomial can be written this way. So P actually decomposes into two parts for the two subsets of relations, and it's just x transpose x minus 1 or x transpose minus 1. So this lives in Cx tensor, and the coefficients are two copies of the matrix algebra. So MNC 2 times. And here x is again n squared indeterminates. So x is xij. And I use the transposition of matrices. So I put the indeterminates in the matrix, so I can use transposition with product of matrices. Okay, so these are the generators and the relations. So then you have to compute the three derivatives, delta p, del p. And this is easy. But yes, first of all, I mean, we need to compute, I mean, actually, yeah, we can compute the rank without calculating delta p of s. So there is a general procedure that relates this rank and the n-to-Betty numbers. So this is done in Shilartenko's paper, and it's easy to adapt it in the quantum framework. So first of all, maybe we have the following proposition. So this is really after Shilartenko. Which says that, I mean, rank of delta p of u is, well, this is, I should write n minus the rank is the usual combination of the n-to-Betty numbers, beta 1 minus beta 0 plus 1. So there are general arguments to make this connection. And okay, and here, of course, we rely on the computation of these n-to-Betty numbers that were done before, as I said. And so this is 1. So if you can apply the theorem, you will obtain indeed one boundedness. Okay. Now there is this second hypothesis, determinant class, which is of analytical nature. In the classical case of a discrete group, you have the so-called determinant conjecture by Luc, which, if it holds, implies that for any polynomials, etc., this will be the case. This will be of determinant class. So in the classical case, you have this very nice tool, and for instance, it's known that the conjecture holds for Sophic groups. So this is a very large class. So you get, in the classical case, in most examples, you will get this assumption for free. But in the quantum case, that's actually the issue, because, I mean, you can, and it's not even completely clear how to state the determinant conjecture in the quantum case, and sophicity even less, I think. And the connection between the two, I don't know. To now, there is no, it's not been developed, that kind of notion. It won't be completely easy to do, I think, because somehow discrete quantum groups are more linear in nature than usual discrete groups. So, and for sophicity, etc., you need some discreteness inside some points. So, I'm not sure. I mean, we tried a little bit and we discussed also with colleagues. But it doesn't seem to be available right now. So, so what we did with Mike is proving this assumption by hand, so to say, and actually it turned out to be a little bit interesting. So let me explain a little bit what goes on. So, well, first of all, maybe what does it mean, a determinant class again? So this is the last missing piece. So delta P of U, determinant class, it's a kind of spectral regularity, if you want. Means that log plus of the absolute value, or say log plus of delta PU star delta PU, should be integrable with respect to the natural state. So here it's H tensor H, then tensor of the usual matrix trace. So this should not be minus infinity. Okay. So log plus here is Luke's modified determinant. So it takes just the usual log, but you impose the value 0 at t equals 0. And so it's, in other words, you have to check that the spectral measure of delta pu star delta pu with respect to the trace here, that the log plus is integrable for this spectral measure. That's what you have to do. Okay. And log plus means that you throw away 0. I mean, if there are additions at 0, you can forget them. Okay, so now we compute delta p of u. Where is the formula? It's not complicated, but still. So the computation is just the result of the computation. So there is a formula looking like that. So delta p, let's just take p1 say first. After the relations. This will be 1 tensor S, u to 3, 1 tensor S, tensor 1, plus u1, 3 star. Okay, so where does this leave? Well, let's say, so this is supposed to be in B of H, tensor MNC. Okay, same dimension. Okay, but here, I mean, for convenience, we identify MNC with the subspace of H. So this P1 of H. So P1 of H is a very natural subspace of H, which is just the ones spanned by the images of the generators. Span of the, say, lambda uij, so capital lambda is the GNS map. So this is a quite natural subspace of H, which is squared dimensional, etc. So S is the antipode, yes. So H, S from H to H is the antipode at the Hilbertian level, but in that case it's bounded, it's well defined, no problem. And U is the matrix of generators, okay. U is in N tensor MNC, the matrix of generators. So, okay, you have a simple formula, and I mean, it's simple, but still you try to simplify it a little bit more. So you see it acts on a tensor product of 3 Hilbert spaces, and using some quantum group tricks, you can in fact reduce it to 2 legs. You can reduce it to something acting on 2 legs. So the proposition is the following one. Proposition delta P1U star delta P1U, which is in fact equal to delta P2 star U delta P2U, is unitarily conjugated to something of the form 2 plus 2 real part of theta tensor 1. So this is in B of H tensor P1H tensor H. So you see I managed to have a trivial action on the last leg. So here theta is in B of H tensor P1H. So we reduce the problem to an operator acting only on 2 legs. And then, I mean, the nice surprise is that we already knew this operator. So this operator is the reversing operator of the quantum Cayley graph. Reversing operator of the quantum Cayley graph. So I will say a couple of words about that. Of F1. What is it? So, I mean, there is a general notion of quantum Cayley graph or discrete quantum groups that goes back actually to my PhD thesis. It's a long time ago, but there is a general notion. But just let me show what it gives in the classical case, just to to convince you that there is some calligraph-like structure behind that. So in the classical case, what is the classical case? In the classical case, you have a discrete group gamma, and you have a symmetric set of generators, okay, inside gamma, finite. Okay, what else? So M is the fundamental algebra, H is L2 functions of gamma, and okay, so so you have generators there, and out of these generators you build a matrix, as you do in the quantum case. So so U, the analog of U, is the diagonal matrix forming by the elements in the generating elements. I put lambda of G, say, because they are acting by left translation on the Hilbert space. G in lambda. Okay, so this is, say, in P of, well, this is in M tensor. It's a diagonal matrix, so let me write down C to the lambda. Okay, and you have the antibody also, so S, the analog of S is the map from H to H that maps G to G inverse. So here I consider group elements as canonical vectors in the Hilbert space, okay, the canonical basis. And then, I mean, you can compute, so I didn't write the formula for theta, I should have written. So theta has a formula which looks like the other one, but only two legs, which is quite simple. S tensor 1, U S tensor S. Okay, so if you try to make the computation in the classical case, so S tensor 1, U S tensor S applies to a vector G tensor H, so with H in G in gamma, H in lambda. So we are in the smaller subspace here. So you take inverses. Then you apply U. So on the right you have the matricial part. So it means that just means here that you select the lambda of H inverse. Okay. So this is S tensor 1. So you select the H inverse and you let it act on the left on the first leg. So you get H inverse, G inverse, tensor H inverse, and then you apply you invert the first leg. So GH tensor H inverse. And indeed, it's like reversing an edge in the Cayley graph. So the Cayley graph has the group elements as vertices, okay? G, an element of the group is a vertex. And it has edges, and let me label them by their direction. So the edge starting from H, G in direction H goes to the vertex GH. Okay? So here we have the starting point in the direction, and it's mapped to GH tensor H inverse, which is the edge starting from GH, indeed in the reverse direction. So if you describe the edges of the Cayley graph by the starting point and the direction, what you get here exactly the reversing operation of edges. And of course, in the classical case, I mean, this operation is involutive. So theta squared is the identity. So H is the sum of two eigenspaces. And in fact, the regularity problem in that case is trivial because, I mean, you take the real part, you make 2 plus 2 real part. So you get a 0 eigenspace and a 2 eigenspace. The 0 eigenspace, you throw it away because it was a log plus. And the 2 eigenspace, you have no convergence problem for the logarithm at 2. So everything is completely trivial. But of course, in the quantum case, the point is that theta is no longer involutive. So it's given by a simple formula, you can study it. So you still have eigenspaces for -1 and +1, which are actually quite large and quite interesting. And actually, I studied them quite a lot, these eigenspaces, in the paper about the L2 numbers. But again, these eigenspaces are not the interesting part for the determinant class issue. So, so what we had to do with Michael is to study this operator on the orthogonal complements. And so the theorem said the main main technical theorem that we proved is that on the orthogonal of these eigenspaces, well, you have to analyze how theta acts, and it's actually a non-trivial matter. But what you get in the end is that, say, the real part of theta is unitarily conjugated again to a direct sum of real parts of shifts. Say R alpha. So R alpha, they are weighted unilateral shifts. So acting on N2 of N, if you want. So up to unitary conjugation. And you have a whole collection, an infinite direct sum of them, actually. And the weights are explicit, you can compute them, but maybe you don't need it, actually. Anyway, so you can analyze the operator. And then it's a problem, I mean, then the determinant class issue is a problem about shifts, weighted shifts, which is something, I mean, this is elementary operator theory, say, and we could solve it and prove indeed that these shifts are determinant class. So the corollary is that 2 plus 2 is part of theta is determinant class. And so, as I stated, using other tools, L of F1 is one-bounded. And I will stop here. Thank you.
Any questions or comments for the speaker?
I'm just pretty general question.
Yeah.
Free entropy can be defined both type free or general.
Well, no, I mean, the definition as it is written down is like, it depends on, you have two definitions. If you work with microstates, it doesn't really make sense in that free situation, because the existence of microstates implies rationality of the state. And also, I mean, if you try to work in the non-microstates setting, you need all the times you use all the times conditional expectations and subalgebra kind of things that do not always exist in type free. So, I mean, yeah. Of course, it would be natural to. Actually, all this stuff about the reversing operator, for instance, holds in the non-Katz case. That we can do with the non-Katz case. But then, I mean, you lack all the machinery of free entropy dimension to prove anything from that. The non-Katz case.
Anyone else? Any questions or comments? Not then. Let's thank the speaker again.